Welcome back, Physics 30. Today's lesson is lesson number 5, Fission and Fusion. So this is the part where things are getting a little bit serious, and at the same time, it's something very practical. If you know some of those stuff like nuclear atomic bomb versus how the sun works, or nuclear power plant and how the star forms. Those kind of practical and at the same time very theoretical, like astronomy, astrology, it's coming in here now. So first thing first, fission and fusion, we need to think about those terms a little differently. Fission in the world of physics means separation and split. Fusion, on the other hand, is a combination. It basically combined together. Before we getting into, we need to understand Rutherford's experiment a bit. Rutherford, if you guys remember, we talk about it near the end of Unit C when we talk about atomic model. He used gold foil experiment. The experiment was very similar as Compton experiment at one point, except Rutherford used alpha particle. So this is what he used. How can alpha particle was used? First of all, he bombarded stable nitrogen-14 with alpha particle. When it comes to gold, he found out there's a direct going towards alpha particle that directly going towards the gold atom, and then it's almost reflect back, something like that. But in any case, similarly, Rutherford bombarded stable nitrogen-14 with alpha particle, and that lead some kind of change in the parent nucleus. So nitrogen turning into oxygen and alpha particle turning into hydrogen, which is proton in this case. He found that two of the parents nucleus turning into two completely different daughter nucleus, if you want to feel in that way. Scientists basically look at this phenomena and found that, you know what, we can create new element, and that's where this field artificial transmutation occur. After uranium, every element should be the one that you see actin and those kind of families. Those are man-made element. It does existed for a certain amount of time, but most of them are short. Like Einsteinium, for example, I believe it was like hundreds of seconds it existed, and it is, you cannot find it in nature, but it exists. It's a different form of it. So it's a man-made atoms is what you need to understand after this. So creating new elements, how can we make that happen? First of all, we need to have very, very high potential energy. Kinetic energy to make the bombardment happen. So you need to use particle accelerator, which is the one that you're gonna see it in lesson number 6 of this booklet. And all elements beyond uranium are artificial, like I mentioned, and none of them are stable. So uranium stays for a long time, but when it comes to after, lasts about several seconds. Let's do a quick example. ES253, I mentioned Einsteinium. This is Einsteinium. Einsteinium 253 isotope is bombarded with a particle. We don't know this particle. As a result, MD 256 is artificially created and a neutron is emitted. Determine the identity of this unknown particle. So first thing first, it's quite a good review. Einsteinium 253 should be on the top, and Einsteinium, which means you need to look at your periodic table, which is one of the page in your data sheet. 99 is Einsteinium. We do not know what it is bombarded with, but we know that one of the daughter nucleus is MD with 101, and it says neutron. Something that you need to understand about neutron is mass exists, it's the same amount of mass as proton, but the charge is 0. That's the clue, and we're basically fill in this blank basically. Now you need to understand that conservation of charge, you can use it to match the bottom number and top number for conservation of nucleon, or mass in this case, if you will. On the right side I have 101, left side I have 99. That means I have two difference. So bottom number is 2. Top number 256 plus 1, that's 266. 253 and 56. That means, 257. That means I have 4 that I need to have as a number, and the particles should be alpha at the end. So 253, 99 Einsteinium plus 4 2 alpha particle, turning into MD256 and neutron. And that is basically one of the example of artificial transmutation. By undergoing this, we have a neutron and another element that we created. Now let's talk about our important, it happened in nature too, it happened in a lot of warfare too, fission. Basically it's discovered in 1938. Like what I said, fission is split. It's a separation. You start with the larger nucleus, it's just split it into 2 smaller nucleus. And the scary thing about that is it can have a chain reaction too. So one famous example, which is also Fermi discovered too, is fission of uranium-235. First of all, some of the people may wonder why uranium play a huge role whenever there's a issue of nuclear weapon and something like that. There is a reason. Uranium is very large and heavy. So that means as a probability way, this atom may undergo splitting because it's very large, very heavy. So basically an atom cannot handle some of those neutrons, and neutrons are inside. And if you want to know the number, look at this uranium-235. Uranium is 92, so 235 minus 92 give you 143. So that's how many neutrons that you have. So no wonder, as a probability way, it can split. So uranium-235, which can be triggered either by itself or, in this case, collide with a neutron. And you don't need a super fast one like artificial transmutation and particle accelerator. You don't need that much. You just need any type of kinetic energy having neutron. And what's going to happen is they will collide together. And think about this as a really big but unstable egg, if you will. Because of this impact, everything is shattered. And the shattering part is basically over here. It turned out this parent, I'm going to put parent in here, gets split into daughter nuclei 1 and 2. Barium 141 was one of them, and kryptonite 92 was another one. And after that, we have these remainder neutron. And the scary thing about this neutron is these guys can trigger other uranium. So when it comes to atomic bomb, the one that's dropped in Hiroshima, it actually have 2 uranium, 2 unstable uranium, and that's about it. The falling and impact basically make that uncontrollable triggering reaction of chain reaction. And if you look at the ratio, it's 1 to 3. So That means these three individually, they may trigger another uranium too. So long story short, the scary thing about fission is these three neutrons, once it released, you don't even need a lot of kinetic energy. These three neutrons can basically trigger new reaction and something like that. So chain reaction can happen. If, however, this is very, very finely controlled, then this is how nuclear power reaction can happen. So, nuclear power plant can generate it. If it's uncontrolled and release massive energy at once, then it becomes what we know as atomic bomb. And energy from the mass defect from these entire reaction, which is delta E is equal to delta mc squared, that can turning into two different type of energy. The very first one, which is obvious one, is kinetic energy of our daughter nuclei and neutron. And this neutron, of course, like I said, can trigger more and more and more. And another is possible gamma energy, and that can be first of all EK 1 over 2 mv squared, and gamma can be HF, something like that. So let's talk about pros and cons of it. Pros of fission reaction. It's really easy. It's really easy to generate even, because the triggering process, you just need low energy neutron. That's it. And at the same time, it does produce massive of energy, mostly heat energy. So that's good enough to make the whole power plant's turbine rotate, because those heat energy can make water turning into water vapor, and that's how we can generate the kinetic energy for the power plant. That is, when it comes to ratio, it's about 2 million times of coal. So a lot of people think about what will be the next substitutional energy source. People mention that. However, you guys probably know when you go to any type of news and so on, even a few years ago, Japan and then the nuclear power plant liquids due to there's many other factors, but one of the main thing is tsunami. There is a huge disadvantage. Number one, how can we deal with radioactive waste? Now, radioactive waste can be interpreted in two different ways. Number one, disposing land and how we do very costly. Environment situation, not only costly but also some other in fact. For example, radioactive decay, and then gamma radiation. These guys can technically distort any type of living creature's DNA structure. So that means it will be effective for future generation as time go. So it may not kill people instantly, but it will affect the future generation for sure. Now, or if it's for a person right now, can make a normal cell into cancer cell, and cancer cell is one of those unstoppable mutated body cell that can infinitely generate it. So have that in your mind. And it's of course non-renewable, because uranium, it will be disappear. And when it comes to gamma and any other radioactive matter, in the end they tend to turning into lead as time goes, but that's another issue. So let's do a quick example. Uranium-235 is bombarded by a slow-moving neutron. It then splits into two smaller nuclei, one of which is zircon-96. If 3 neutrons are also emitted, determine the other daughter nuclei. So let's do this question. Parent first. and it said it's collide with a slow-moving neutron. And that's everything on the left side. On the right side, we have daughter number 1, which is zircon 96, 40 at the bottom. We don't know what's in here, but we have 3 neutron after that. So let's look at the bottom number first. If I look at the bottom number, 92, 0, 40, 0. So 3 times 0 is 0, so we don't need to consider this neutron as a byproduct. And for the chain reaction, let's rather look at what we have. 92s are the number that we have on the left side as total. So we need to make 92, thus bottom number is 52. And 52 was thallium, Te. Now next, if you upper one is a little tricky, so you can put it this way. Left side together, 236, that is equal to 96 plus x plus 3 times 1, which is 3. So x, from, simple isolation of numbers, you're going to find out that is equivalent to 137. Because it's like 236 minus 99. So 137. And that is basically one of the missing daughter nucleus. Now, let's finish this up by undergoing our last part, which is fusion. So, fission is easy to undergo because, not easy to undergo. It's rather easier to make things happen. Fusion is not that easy to do because of one fundamental force in our universe, which is strong nuclear force. Basically, think about strong nuclear force as a super glue. You have to make proton together, which is completely opposite as what we learned before. How can I make plus and plus stay together almost next to each other? That itself is impossible if you look at electric force. However, the one that make that happen in the nucleus with the neutron and those kind of thing at the center of every atom is basically known as one of the fundamental forces, strong nuclear force. Basically, fusion means we have to have small nuclei fused together. So it's opposite of fission. You make 2 parent nuclei to make 1 daughter nucleus. So that is an example. However, this is almost impossible to do without any thorough preparation because of 2 things. You require huge amount of energy, and number 2, such an enormous heat energy is coming out from this process. Everything will undergo meltdown. So it's one of those specific study that we are doing. Although we are using nuclear fission for running nuclear power plants, if we can find this way, nuclear fusion, we don't need to worry anything about, toxic waste and so on. And I'm going to go through that after this specific example. And what happened is, it happened in this universe, it's happened in the star. Hydrogen combined to make helium. It's a natural reaction. So the one important reaction that I'm going to show you is a sun, and it involves deuterium and tritium. Deuterium, like the word suggests, it's like, in the song duo, that means 2. Tritium, tri means 3. So what does that mean? That means deuterium is basically hydrogen 2. So that's one of the isotope. Tritium is hydrogen 3. So you have one neutron, 3 neutron, something like that. When they collide with extreme high speed and with a lot of energy, then what's going to happen is those two, and if you think about it, hydrogen, hydrogen, that's proton and proton, right? They hate each other. They tend to not stay together. But if we overcome that and then try to bond them together, imagine the repulsive force, and at the same time building them up together and make them bond like a super glue. That part requires enormous energy to start with. But in any case, it will create neutron as a byproduct and helium, or alpha particle if you will. It's a stable daughter nucleus. First of all, compared to previous situation, it's quite clean product. Unharmful. It's noble gas, in fact, right? And energy is a lot of energy. And of course, this reaction happens all the time in any of a lightning star, like sun. So energy from the mass defect throughout this situation. So delta E from delta mc squared turning into two different formats. One of the format is basically use it for kinetic energy for neutron and nucleus. Another one is gamma photon. So basically this energy, it also have heat energy, but let's just put that E is equal to HF situation. And when it comes to this EK, which is 1 over 2 mv squared. Pros and cons. When it comes to pro, abundant. Hydrogen is most common element in the universe. Very, very, very abundant. Next, it's very stable byproduct. It's so stable, in fact, that it's more than harmless. You can even use it as an alpha particle and those kind of things. Even a balloon, if you will. Disadvantage, uncontrollable temperature. It's 10 to the power of 8 Kelvin. And that's how much are required to make these happen. So if you think about cost effect, why people choose nuclear fission is because it's relatively cheaper to do. This costs more money than create money, ironically. And that doesn't mean we should stop. We imagine we can generate this chemical reaction that happened in the sun that have been happening for billions of years. And imagine we can somehow make that work on Earth, then we can create vast energy that every humanity can use. I was a little bit more passionate at the end, sorry about that. But that is probably our next goal for humanity. How can we use energy very efficiently? And at the same time, it's a Nobel Prize question, basically. That is today's lesson. Your to-do list says do questions on page 22 of this booklet and 23.